at least to my class. I'm Robert Chabal, or Rob. And this is section 1244, 1B. This is the Canvas page if you haven't seen it yet. I have to update this a little bit, which I thought I did. Although there's actually, do you know, normally there's 16 weeks plus spring break, which makes 17 weeks. But now we have a final on the last week, which makes it 18 weeks. And so there should have been a week 17 in here with the final exam. We only come for one day of week 17. And I thought I put the correct syllabus in there, but now I realize that I was working on fixing my syllabus, and I guess I failed to save it. And then this is a school computer, and the school computer, they do updates. When they do updates, it wipes out all the work in progress, and it got deleted. And so that's what I think happened here. And so I had the corrected syllabus. Now I just looked on my computer and it's done. I just have the old syllabus in here. The old syllabus goes up to week 16. And let me just start off at the end first. We have one more week after this. And so here on June 12th, is Thursday, then June 13th is Friday, which is graduation. And then that's 14th, 15th, and then on Monday the 16th is our last day. Did you guys see that? And so we'll be here on the Monday after this week. And so what I decided to do is Monday is our lab day, it's a long day. And so originally on Wednesday I was gonna have the multiple choice portion of the final. I like to split the final into two parts. So the multiple choice part, which is the bulk of it, and so it's gonna be 3 hours. And then this, and it's an hour and 25 minutes, which would be the free response. So we'll do this this free response part first, and then on Monday, we'll do the multiple choice. And so what I'm gonna do is I'm gonna redo the syllabus again and then spit it up. But essentially it's just moving this to Monday and then just spreading things out a little bit. Okay. So I'll need to fix that. Well, what we're doing today, this is correct. Well, we're having our class intro and we're going to review some chemical properties here. Most of the semester is going to be devoted to chemical properties or chemical reactions. And so even chapter 24 here, chapter 24.1 and 24.3, we're looking at Lewis acid-base reactions. And then 16, 17, 18, 19, we're looking at other chemical reactions. And one of the things we want to be able to do is predict things. Predict if a reaction is going to occur. Is there a driving force? And not only that, we want to predict the extent of reaction. And so there might be a driving force present, but how much of it is going to react? Will all of it react? In Chem 1A, it was either black or white. It was either all of it reacts or all of it being the limiting reagent, whatever the limiting reagent was completely consumed. In Chem 1B, that might not be the case. We have the limiting reagent. In Chem 1A, we'd assume all the limiting reagents consumed in a chemical reaction. In Chem 1B, we can't assume that. Some reactions don't have enough oomph to make it to the end. They just partially react. And so that's what we're going to be focusing on here, these partial reactions. And that's going to be 16, 17, 18, 19. And then we're going to drop back down to 13. So 16, 17, 18, 19 are mainly like predictions based on observations. People took observations, they saw how much reacts, and then we can make predictions based on that. Chapter 13, we're going to try to approach it more from a theoretical perspective, predictions based on thermodynamics. So that's it. in addition to driving force, we want to understand how fast the reactions occur. You know, some reactions occur very fast, like explosively fast. Other reactions are so slow, it's essentially no reaction. And so that's the topic of chemical kinetics. So not only do we want to know what the driving force is, we want to be able to predict how fast things should occur or not. And so that's chapter 15. And then we go to chapter 20, which is electrochemistry, which is redox. So this is just more reactions. And this is a particular application of redox reactions. We can use redox reactions to store energy or generate electricity, i.e. energy, electrical energy. Or we could use electrical energy to drive reactions. You know, maybe it needs a little oomph to get to the top of the hill. We can use electricity to get it to the top of the hill. Thing. That's chapter 20. And so these are all chemical reactions. In chemical reactions, the most important fundamental force is what? Gravity? Do chemists care about gravity? No. Nuclear forces? No. Chemists don't care about. What do chemists care about mostly? Electrical forces, you know, plus, minus, Coulomb's law, that kind of thing. And so just positive, negative attractions. That's all chemistry, just these positive and negative attractions. Nuclear chemists don't care about positive, negative attractions. You know, nuclear chemists don't pay attention to electrical forces because there's a force that's much more powerful than electrical forces, and that force are the nuclear forces. Nuclear forces like the nuclear binding energy. You know, nuclear binding energy holds all the protons together. Electrical forces would say the protons would all fly apart, you know, because they're all positively charged. They're going to repel each other. And so in chapter 25, at the very end of the semester, we're going to talk about nuclear chemistry. And so we just shift our thinking there. But we're going to look at nuclear reactions, nuclear properties, that kind of stuff. All right. What I decided to do for this semester is I'm not going to have like regular midterms. Well, we're going to have our like chapter exams. And let's say I finished chapter 24 here. Actually, I split chapter 24 into two parts. And so part 1 of chapter 24 exam would be like this week here. And then we're going to come back to chapter 24 here later in the semester, kind of at the very end of the semester. In part 2, the chapter 24 will be rolled into the final exam, most likely. I don't think I'll have a chapter 24 test here. But since chapter 24 is divided into 2 parts, then this is going to be worth a little less. You know, it's only 3 sections, 24.1 to 24.3. And so we're looking at these Lewis acid-base reactions that form special, what we call adducts, ADDUCTS, or complexes. So these are called coordination compounds or coordination complexes or coordination ions, kind of thing, complex ions. And so chapter 24 will have, let's say, tests sometime this week. And then we finish chapter 16 next week, and then the following week we'd have a chapter 16 exam. And so the first part of chapter 24 homework will be due on the day of our test here, and then chapter 16 homework will be due on the day of the test here. And I leave it kind of flexible, so it depends. If I get behind, I can adjust the schedule. And so our exams are just going to be following, when we finish each chapter. Those exams are going to be worth 50 points each, except for this. This is going to be worth less. We're going to have some quizzes interspersed here too. Those aren't marked on the syllabus, but those.
Regarding those quizzes, are there like usually warnings given?
Mm-hmm.
Okay, gotcha.
So we'll have a quiz this week. I'll tell you more when we get further along. The lab days are Monday and Wednesdays, except, these first 2 weeks, I'll just kind of catch up with the lecture material, and then we'll start the lab, let's say, Wednesday, the 26th here. But this will just be a check-in and safety. Our first real lab will be the third week here, Le Chatelier's principal. And so you'll need safety goggles for this and appropriate clothing and closed-toe shoes, that type of stuff. So we'll have a lab here, and then for this particular lab, the report is pretty simple. You just fill out, or it could be observations. I might just look at your observations and check those off, or you might fill out a short report form for this particular lab. Normally, the lab reports are due a week after we do the lab. So if we finish the lab here, the report will be due here. Same thing here, we finish the lab here, the report should be due here. Some of the labs are a bit different, like the synthesis of a transition metal complex. This one, I'm not going to have a simple short report format sheet that you fill in. This one is going to be a formal scientific report, and so I'll talk more about that. This first one we'll write together, synthesis of a transition metal complex. This is actually a 3-day lab, so we'll finish it on this day. On March 17th, we're going to weigh the product here and then start a new lab. New lab would be pH titration. So we're going to do a pH titration where we titrate an unknown acid and monitor the pH as we go along, the power of the hydrogen ion concentration. That's a 2-day lab. This one will also be a formal report. This one's going to require some data analysis. So this is going to carry on over to March 24th. Here we're going to go in the computer lab, Chem 108, and then do titration data refinement. Data refinement, that just means data analysis. So we're going to graph it, basically. And based on this graph, we're going to identify the unknown acid over here. So we'll have another day in the computer lab. We're going to generate lots of different graphs so we can try to analyze it in different ways, the data. And then sometimes it's easy, to identify the acid. Sometimes it's difficult if, the data conflicts. Hopefully we don't get any conflicting data. Like some data says it's this acid and other data says it's that acid. So which acid do you pick? And so depending on the data, then we'll figure it out. Some data is more reliable than other data. Okay, so this is going to be another formal lab write-up. And then we start qualitative analysis. If you took Chem 4 here, you did some qualitative analysis. It's very similar. And so we're going to have multiple days of qualitative analysis. Actually, a bunch of days. Here, 6 days of qualitative analysis, roughly. That one's not going to be a formal report. That's just going to be a simple lab write-up. Okay, we might miss, actually, a day here. On April 10th, can you make a note here? April 10th, I have to leave out of town on this date. And so April 10th, what I'm going to do is I'm just going to post a video lecture on chapter 13 here, but I will be gone.
Will you be recording all your lectures again?
Yeah, I'm trying to record all my lectures on my iPhone. Was that, I don't know, from last semester, were the iPhone videos okay or not?
I still prefer the computer ones, but...
Okay, do you prefer the computer ones where I wrote on the computer here?
Yeah.
With the tablet? Okay. Actually, I'm thinking about switching back to the computer ones as long as I can get it to work on this, because we have a budget shortage, and the budget shortage asks us to conserve the pens here, and so we're going to, I have to cut back on the usage of pens right now, and so I'm thinking of just doing it
You're
here.
gonna get a chalkboard again.
Chalkboard, yeah. Maybe apparently there's a lot of, they go through boxes and boxes of these pens, and so we had a meeting last week, so that's one thing. So yeah, I'm planning, I'll start that. I'm just gonna write on the overhead projector. Tablet. Not overhead projector, but on the screen. All right, so, yeah, like I said, I know I can't make it this day, April 10th. And so no class on this day, but there's going to be a video lecture if you can watch that, so I don't get behind. All right. That's right before spring break. The other days, can you put an asterisk here? May 14th, 15th, and 19th. Unfortunately, I might have to miss these days here. So if you put an asterisk on 14th, 15th, and 19th. And so, since there was a chance I might have to miss it, these were just computer things. These computer things that you could do. I left it kind of ambiguous. That depends. It's most likely computer days that we were going to use to write the report, but you can write it using one of the other computer labs here as well. But the 14th, and the 15th, I will just have a video lecture here if it's the case that I'm gone on these days. Other than that, it should be here. So again, 14th, 15th, and 19th, there's a chance I have to go. And the 10th, I'm definitely have to go on that day. All right, so we go through, we're doing the qualitative analysis. Qualitative analysis, we're just trying to identify the unknowns and some solution or solids. We're doing both solid and solution unknowns. So we'll have a number of unknowns that you just test. Okay, then we have this Visual Mintech. Visual Mintech is a free software package that does calculations. So we'll have a couple of days of this. The report will be very simple. It's just a printout of your Visual Mintech data. And then on the 5th here of May, we'll have the rate law determination day 1. This is kinetics. And so this kinetic experiments, this will be a formal write-up as well. So we're going to go to the computer lab again and graph all the data. And then I have another day in the computer lab, or a couple of days in the computer lab. We're going to graph the data and then determine what we call the rate law. You know, it's just rate law is just a mathematical equation that defines our kinetics, and then write a formal report for this, which shouldn't take too much time, I think. Okay, then we'll have an electrochemistry experiment here. This is just a simple report. It's probably just, this is not even going to be a report. It's just going to be your observations in your lab notebook, basically. The same thing with molecular models. Molecular models will just be like a participation thing. You're just going to build three-dimensional structures of transition metal complexes from chapter 24. And so there's no report for that. All right, I moved the lab cleanup to June 11th. I redid all this, like I said, but for some reason it got deleted and I didn't upload it. So this got moved to here, and then there's some more review. So I'll post that later today, the updated one. So don't print this one out. All right, so as far as office hours go here, that's blank. But I did post those on Canvas. So let's take a look at this link here. And so my office hours are going to follow the morning lab. The morning lab ends at 12:40, so this will be 30 minutes. And then the afternoon lab ends at 4:20, so from 4:20 to 4:50. Yeah. Tuesdays, I'm going to have a Zoom, and this is my Zoom number here. and just log in Zoom. 9:30 to 10:30, it's a bit late. I could change it if there's enough demand. On Wednesdays, it'll just follow the morning lab and the afternoon lab. And so what this means is you can work, if you want to work later, at least 30 minutes later. You need extra time. Also, if you need extra time, you can attend the morning if there's room. I think there'll probably be room. The classes aren't terribly impacted this semester. Okay, the office hours are going to be held in 103, this room, or 162 is our lab room, or 120 is my office, or 108 is the computer lab. And so I'll be in one of these, except for the Zoom. There I'll be home. You can reach me there. Okay. No, that's not what I wanted. Okay, let's look at the course breakdown. No, it's not there. It's here. Under the syllabus, I have the course breakdown here. All right, that's my phone number, email. You need to contact me. There's a catalog course description. The course objective, student learning outcomes, just a couple of them, we have lots. Okay, required materials. We're using the 12th edition. It's kind of weird. If you go to the bookstore, they only have the 11th edition. It's not that, I guess, not that many schools use Petrucci. And so I think they didn't bother printing out the hard copy version of it. But we like Petrucci because Petrucci is kind of at the appropriate level, you know. So for example, UCLA, if you take general chemistry there, they use an honors level book. The honors level book will have calculus in it and other stuff, and it approaches the topics a little bit deeper, but you know, they have higher prerequisites. They expect everyone to either be in calculus or have had calculus, you know, when they take general chem. And so that's too much for us. So we want to step down, but we don't want too big of a step down. And so Petrucci is just a step down. It doesn't have that much calculus in it. There's a little bit of calculus in there, but it doesn't have zero calculus in there. And so you don't need any calculus for this class. You just need algebra, but it's there as a reference. So anyway, some of the other texts out there, like I'd like the no cost one for sure, but the level is a little bit down, so it means that there's a bigger step up to the next class after general chemistry, which makes it difficult because the next class after general chemistry typically is, well, it's organic, but in the physical or the general chem side of things, it's much harder, you know, like a junior level class at UC. And so this is a nice level. And so, do you need the 12th? You can get by with any edition of it. Since I'm doing Mastering Chem for the homework, it doesn't really matter if you have the 12th edition, 11th edition, or whatever edition, it's fine. I'm not doing any end of chapter. Usually they do these, you know, like the difference between the 11th and 12th edition, they added some features. And then they switch the homework a little bit, but essentially it's the same problems. But it gives a reason for people to buy the new book rather than the used book, so they like to do these. Although the content of the material hasn't changed much. So 11th edition is not a problem if you have that, or earlier edition. The homework is not going to be from the book, though. The homework is going to be from Mastering Chem here. And I assigned mainly tutorial problems. When there wasn't one for the appropriate section, then I did an end of chapter problem. But it's all contained in here. All right, so this is required. Unfortunately, Master in Chem has some cost associated with it, but if you have it from last semester, you shouldn't have to pay for this semester. I think the Master in Chem license is good for 1 year, so you can just add this course to that. You'll need a composition notebook. If you got one of these from last semester, then just use it. Well, you should have plenty of pages for Chem 1B. We're not taking that much data. And so quad ruled with some binding. At the bookstore, they have a stack of quad ruled composition notebooks this tall. It's in the arts and engineering section of the bookstore. If they're out, then you could just get a college ruled. A quad ruled is just graph paper ruled. Safety goggles from last semester are fine. Most people have visor goggles. Works well. The scientific calculator. One thing about the scientific calculator is if you could get one that has an equation solver, like quadratic equation solver. We're going to be solving a lot of quadratic equations this semester, and it's best if you don't have to do those by hand. If you could just do those punching A, B, C into the calculator, it's save you a lot of time. And so that's important for the homework and also important for the exams. But I try to write the exams to give, for those that don't want to get a quadratic equation solver, I try to write the exam so that you have enough time to solve it by hand, the quadratic. Okay. The only thing is, it's a pain, because let's say if A was 4 sig figs, like 1.238, then you're carrying that all through the entire quadratic equation. It just becomes cumbersome. If you had simple whole numbers, it's a lot easier. And so I think it's worth it. The calculators that solve quadratics or have equation solver, these are non-programmable calculators, like $20, I think. A Sharpie, we have some Sharpies in the lab, but if you want your own, bring it. If not, I had it as required. I should have that as optional. But I don't know, because the budget, they're probably gonna cut the Sharpie budget too. They cut the pen budget, so next is, that'll be on the, but we'll see. Recommended materials, Sharpie, lab coat or apron, nitrile or latex. I recommend nitrile gloves. Nitrile gloves have much higher degree of chemical resistance than latex gloves. And they're more breathable, so they're a lot more comfortable.
Professor, 2 questions. One on the scientific calculator. Are graphing calculators allowed, or do you just want a certain?
The official department policy is graphing calculators are not allowed.
Okay.
Yeah.
Gotcha.
Are graphing calculators allowed on standardized tests now? Because our department policy was to follow whatever the current state. I think they are allowed. Like on the SAT, are graphing calculators allowed? We might have to change it, but the current department policy is they're not allowed. If you don't have the reason why they have this policy is to prevent cheating. Like I was giving a nomenclature test one time, and the person had their scientific calculator out, and they were scrolling down through it. And I'm thinking, nomenclature test, why do you need a scientific calculator for a nomenclature test? So they're scrolling down because they had the name and the formulas of all the ions in there. So that's what they're doing.
And then second question, will the quizzes mostly be based on the information from the Master in Physics, or should we expect them to be?
No, the quizzes are going to be based on the lecture material. Just what we're covering in class.
Gotcha.
But we're going to have a quiz this week. I'll tell you what it is, and the format of the quiz.
Quiz or test?
What?
Quiz or test?
When's the quizzes and tests?
Yeah, like when do we have quizzes? Like,
We're going to have a quiz like every week.
okay.
We're going to have a quiz and a test, probably, or just a quiz. Depends on the timing. The quizzes, The quizzes are a little bit different, though. The quizzes are like kind of like worksheet quizzes, where you could work with other people and then turn that in. Whereas the test is just individual work. So the quizzes are kind of just group quizzes. All right, required assignments here. I don't have any drop quizzes or dropped exams here. So, or dropped labs. Just because all the labs aren't the same. If you do miss a lab, try to make it up in maybe the morning lab section or in somebody else's section. Quizzes will probably be easier because those are group quizzes. I'll probably collect them up. Probably won't collect them on the same day. I'll probably let you take those home, collect them later. Exams are going to be a bit more difficult to make up. I'll see we'll just take it case by case. If that happens, hopefully it doesn't. But assuming I stick to this, the quizzes aren't going to be weird. The quizzes are going to vary as far as points go. I have 5 points at times 10. We'll have 16 weeks, 16 weeks plus a day. And so I might have more quizzes, we'll see, fewer points. But this adds up to 1,000 points. So the final's worth 20%. The labs are only worth 18%. Homework's worth 10%. And your exams and quizzes are worth more than 50% of your grade here. The score breakdown, 88% and above will be an A, 78 is the cutoff for C, 78% is cut off for B, 65% is cut off for C. The D cutoff is 50%, but if you take the final exam and you're below this, I'd give you a D, if you're in that range. Hopefully you aren't. All right, because of our UC articulation, at the UC, the lecture and the lab are 2 separate classes. So you can do great in the lecture and fail the lab. That's not a problem there. Here, my lab is only worth 18%. And so in theory, you could just skip all the labs. The lab is a lot of work. Skip all the labs and still pass the course. Could get a B, potentially. Because of that, the UCs require us to do this. The UCs require us to treat the lab as a separate course. And the problem is it's not really a separate course. So they want us to treat it like a separate course. So if you fail lab, you failed lab, but we can't say you got an F in lab and you might have gotten like an A in lecture. Here, if you fail lab, you're gonna fail the entire course since we don't do separate lecture and labs. And so this is a weird thing with our UC articulation. And so make sure you attend the lab. It's important. Okay, a note on cheating and special requirements or needs. And changes here. Any changes will be announced in lecture, mostly, or possibly on Canvas. We also have the dictionary definition here of chemistry. Chemistry is the science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems. But here, when we think about reactions, these are chemical reactions. Chemical reactions are just chemical properties. Chemical properties and chemical reactions, same thing. And so this is a little bit, this isn't the way chemists would define it, because chemists define properties as either being physical or chemical. Here in this definition, they're just treating these as physical, and then they have the chemical properties over here as reactions. And so we're going to be focusing a lot on the reactions of matter. But to understand the reactions of matter, there are different ways we can predict chemical reactions. One way we can predict chemical reactions is by a pattern, like AB plus CD. Have you heard that? AB plus CD yields. Yeah. That's one way. And so you memorize a whole bunch of patterns, but that's too much, because how many different patterns are there? You have AB plus CD, and then you have A plus BX. What other patterns do you have? A lot. And so to try to minimize the amount of patterns that we have to memorize, we want to approach things more theoretically. And approaching things more theoretically, we want to see how the composition of the structure affects the properties. And so what we're going to do here is review some chemical reactions. So this will be week 1 here. And normally I'm not going to use PowerPoints, but for this I'll use PowerPoints for this review. And these are the same PowerPoints I use in Chem 1A. So we talked about the dictionary definition, and then I talked about physical and chemical properties here for reactions. I'm going to skip some of these slides. Then we come to this. So we're going to take a look at the properties. Mainly the chemical properties. This is what we're looking at. And there are different approaches to it. So, for example, if you want to know, will this substance A react with this substance B? So will A and B react? Well, the different things you could do, you could take A and mix it with B, and then C. Do they react? And so you could just measure it or observe it. And so what we could do is we can take observations. And then we might see some kind of pattern, or we might not even bother with a pattern. Who cares if there's a pattern? Just see if A and B react. You take A, mix it with B, does it react or not react? If it reacts, what does it form? Right? And so we can skip that here. Or we might see a pattern. Well, AB reacts and form A plus B forms AB. Well, that's a pattern. And we can use the pattern to predict what the product is, right? But there are too many patterns out there, You just learned a few, right? I don't know, it depends on who you had for Chem 4 and Chem 1A. Chem 4 is the intro, you might not have even had that here. But in Chem 4, we're required to teach 9 patterns, The 9 patterns, they are. I didn't bother teaching those. So if you had me for Chem 4 and Chem 1A, I didn't even teach those. And so you might have 9 of them, but there are a lot more. And so it's not the most powerful approach. I think the most powerful approach is to, this is approaching it from observations, measurements. A more powerful approach would be to approach these properties more from a theoretical perspective. From a theoretical perspective, we're looking at, the composition, what is it made out of? That'll tell us. And the structure. Because ultimately, we want to understand the properties. So if we use the composition and structure, then we can correlate those with properties. And so this is more of a theoretical approach. This is more of an observational, experimental approach, and so we call it experimental. But do you want to do everything by a pattern? If somebody comes and asks you, will A react with B? And then you say, oh, wait a few days, maybe a week, I'll go to the laboratory and do it, and then I'll come back with your answer. Do you want to do everything like that? No, it would be nice to be able to come up with some kind of theoretical approach. That way we can avoid having to actually measure it. And so the goal of chemistry is that. The goal of chemistry is understanding this deeply enough that maybe we don't have to go in the laboratory and actually measure it. Maybe we could just predict it based on theory. So understanding the properties, mainly chemical properties here. I'm not going to really get into the physical properties. Understanding the chemical properties of matter based, well, we can do physical properties as well, based on composition and structure. Unfortunately, we can't do everything. You know, sometimes the theoretical approach is too difficult. You know, we have to mix. You know, we do a combined approach. You know, the combined approach would be we know some experimental observations that we can use to help predict, and we know something about the composition and structure, and we put those two together to come up with a prediction for the properties. Or if we see some properties, then we can try to correlate those with the composition and structure to better understand it theoretically. When I talk about this, I'm thinking in terms of the scientific method. In terms of the scientific method, this is the way I typically think of the scientific method, but it doesn't have to follow this route. What do scientists do? Well, scientists do a lot of observations. They take a lot of measurements. Observations / measurements. They observe nature. And scientists are good at observing nature. But what are they looking at when they observe nature? Well, you know, sometimes things look pretty random, but even if the things look pretty random, they're trying to find patterns in that randomness. You know? And so they look for patterns or trends. And let's say I notice a pattern. I notice a pattern AB plus CD yields AD plus CB. And I might call that the law of AB plus CD. I would, because if that pattern is a very solid pattern and consistent, then I could get a law, you know. And so laws would have to deal something that has or is quite reliable. And so the question comes up is, are there a lot of exceptions to the law? If there are a lot of exceptions to the law, then we probably shouldn't call it a law. Maybe we should call it a rule. You know, rules have lots of exceptions, but laws shouldn't have too many exceptions. And so we come up with a new law called the law of AB plus CD, but AB plus CD has too many exceptions, so we're not going to call it a law. We're just going to stick with patterns. And so that's what we're looking at here. We're taking observations, we're looking for patterns, and with these patterns are going to be patterns and properties. And then we're going to try to correlate this here. And so, you know, as we better understand these chemical properties, then we might actually go to here. But patterns and trends is enough here usually. But what we want is a more fundamental or more theoretical understanding of things. And as we go beyond the law, we come up with a hypothesis. A hypothesis is your initial theory or theoretical understanding of this. It's a tentative theory. That's what a hypothesis is, a tentative theory. Eventually, when the tentative theory has been subjected to scrutiny, that is, it's been tested, then the hypothesis becomes a theory. A theory is something that's got widespread acceptance. So a theory is the ultimate goal. A good theoretical understanding of chemistry, then we should be able to predict patterns. We should be able to predict laws. We should be able to predict observations by going backwards here. Although we skip hypothesis, because if we're already at the theory, then the hypothesis has been proven, you know, quote unquote, then we can predict these types of things. And so we can think of it in terms of things like the ideal gas law. The ideal gas law is PD equals nRT, and that came from patterns of gas behavior. PV equals nRT, well, that's just a law. What we want is we want a deeper understanding, a deeper fundamental understanding. So we might come up with a hypothesis and eventually a theory. And the initial hypothesis is that gases consist of little particles, and these particles are all moving around. And that eventually that hypothesis turned into kinetic molecular theory of gases. In kinetic molecular theory, we can derive the ideal gas law, so we can derive the ideal gas law from kinetic molecular theory, or we can derive the ideal gas law just based on observations. Yeah. Now, it's good to be able to do both ways. Same thing with chemical properties. You know, with chemical properties, it'd be good to be able to derive it from just observations, patterns, or the opposite way, from a more theoretical approach here, based on composition and structure. Okay, and so this is the mix. Use a mix of theory and descriptive or experimental chemistry. We'll skip this slide. I'm gonna skip this slide too. Skip this slide. Skip this slide. So as I recall, we have to give 9 patterns. Or so in Chem 4 for you to recognize. These patterns are called combination, you know, A, B, A plus B is AB kind of thing. Decomposition, acid base, single replacement, double replacement, combustion, precipitation. This is 1, 2, 3, 4, 5, 6, 7. Which 2 am I missing? Did you have them memorized at one time? Do you know which 2 I'm missing? This is A plus BX. I'm missing this one here, which is non-metal oxide plus water, or non-metal oxide plus a compound. And the other one is a metal oxide. A non-metal oxide plus water yields an acid, and metal oxide plus water yields a base. Those are 2 additional patterns. I didn't bother with any of those, teaching those, because there's some problems with those patterns. And so what I like to do is, yeah, these are great little subcategories, but combination, you know, they're different kinds of combination reactions. So we have subcategories of combination reactions. And we have to make sure we're in the proper subcategory of combination reactions to understand it. And so that leads to more subpatterns and more subpatterns. And so pretty soon, it's not enough. 9's not enough. If you're going to memorize patterns, you got to memorize a heck of a lot more than 9 in order to be successful at predicting chemical reactions. Well, that's if you want to subcategorize the chemical reactions as simple patterns. But what I do here, and this is the same as Chem 1A, I just take a step back from this. This is too many. Too many. And not only that, you have to memorize all the exceptions. Remember I said, okay, you know, we could call it a law, but there are too many exceptions. You know. And so what do you do with all the exceptions? Well, if you're going to memorize a pattern, then you better memorize all the exceptions. And then pretty soon you have an overwhelming amount of work to do. And so what's much better is if you had a theoretical understanding. That's great, but getting the theoretical understanding is, how do we get it? It's not so easy. So what we're going to do is we're going to change the types of patterns here. So rather than having this huge number of patterns, I'm going to simplify it into just 3 patterns. And so when I look at this reaction here, what type of pattern is this? Well, this is an AB plus CD plus E. Do you know the AB plus CD plus E pattern? Have you memorized it? Probably not. Do you need to memorize it? Well, it depends on what approach you want to take. If you want to take the simple approach of memorizing pattern and hope it works and it's not an exception, then yeah, you need to memorize it. Or what we're going to do is we're going to reclassify that. You know, this is a very famous reaction. This AU is what element? Gold. Gold, one of the physical properties of gold is very hard to dissolve. You aren't going to dissolve in water. It's insoluble in water, which is a good thing because gold's quite expensive. But you could try to dissolve it chemically, and taking advantage of chemical reaction. So if you use this acid, which is, what's this acid? Hydrochloric, it's not enough. Hydrochloric is not enough to dissolve gold. If you use this acid, what is that acid? Nitric acid, it's not enough. So nitric acid is not enough, hydrochloric is not enough, but in combination, it's enough. So if you combine hydrochloric acid and nitric acid, then it's enough to dissolve gold. And this mixture, this combination is called aqua regia. Aqua regia stands for royal water. And so this is royal water. Royal water is used to dissolve gold. Now, how does it dissolve gold? Well, I have things divided into 3 patterns. So when I look at this, this is a bit more complicated. But the first step of this is a 2-step reaction. The first step is nitric acid. We use nitric acid to oxidize the gold and form gold 3 ions. But the problem with gold 3 ions is it's terribly unstable. And so this is why we need the hydrochloric acid. And so the nitric acid is what we call an oxidizing acid. It's a powerful oxidizer. It can oxidize the gold, but the gold 3 is terribly unstable and it is going to revert back to gold unless it's attacked by the hydrochloric acid. Now, the interesting thing about hydrochloric acid here is it's not acting as an acid. You know what hydrochloric acid is acting as? It's acting as a base. But how can hydrochloric acid be a base? It's a strong acid. Well, the reason it's a base is it's because it's a Lewis base. Bronsted acids and Lewis acids H+, but chloride is a decent Lewis base. Now chloride, as far as a Bronsted base goes, is terrible. So if we look at chloride on the middle chart there, it's so weak we don't even consider it basic. I mean, it's weaker than water as a base. And so chloride is what we consider a neutral Bronsted base, but as a Lewis base, it's okay. And so the chloride attacks the gold 3 and we form a gold complex and we can dissolve gold metal. And so by using a different pattern system, by just recategorizing the reactions is a little bit easier to understand. It might not be so easy right now, but once you start doing these, it'll be easier. And so it's not comprehensive enough. We don't have enough patterns, and there can be a lot more reactions out there. And then number 2, it can be confusing because both of these can be classified as combining 2 reactants to form a product. So here we're combining 2 elements, here we're combining 2 compounds. And so both of these can be considered combination reactions because it's just taking substance A plus substance B to make substance AB. Substance A plus B makes this. Although this is a little bit more complicated. And so we'll have element plus element combination, and then we'll have compound plus compound combination, and element plus compound combinations. Do you want to memorize all of those? No. You know, and so what we're going to do is we're not going to call these combination reactions. The first reaction here is what we'll call a redox reaction. And the second reaction here is what we're going to call a Lewis acid-base reaction. And so when I classify this as a redox reaction, that looks just like all these other redox reactions that we deal with. There's an oxidizer, there's a reducer. And when I look at acid-base, this looks like a bunch of other acid-base reactions. You know, when we do more acid-base reactions, we see CO2. CO2 is weird. CO2 we typically think of as being a pretty decent Lewis acid. You know? And so we start thinking in terms of that, whereas this is a Lewis base. So in light of this, I just want to divide things into 3 types of chemical reactions. These 3 types of chemical reactions are going to be based on the driving force for the reaction. So all metathesis reactions, and there could be lots of different patterns of metathesis reactions, but they all share one thing. They're all going to share the same driving force. So that's what we look for. We look for, is there a driving force for forming those products? and then we can determine that. And the same thing with acid-base. But acid-base, there's really one comprehensive definition of an acid and base, and that would be Lewis. Lewis covers the entire universe of acids and bases. And then if you look in the entire universe, there's one little solar system of acids and bases. Those would be the Bronsted acids and bases. So do we want to deal with the entire universe or just that one little solar system or galaxy or whatever of acids and bases? And it turns out that, yeah, it'd be nice to classify them as all acid bases, and but in this case, I told you I don't like all these subcategories, but we're going to have to subcategorize this, because if we treat all acids and bases as Lewis, it becomes more difficult because of the driving force. Here, if we look at that one galaxy of acids and bases called the Bronsted acid base, then it's a lot easier because we can just use that chart in the middle there. And all those Bronsted acids and bases are Lewis acid bases as well. But we think differently. So when I have a Bronsted acid base reaction, I think totally different than if I had Lewis acid base. And so that's the reason why. And so this is going to be subcategorized into two. And then we have oxidation reduction. And here we'll have more subcategories depending on the type. But three basic types. There are others. That's why I have this little asterisk. The others would be like photochemical. I don't know if you can read that. It's so small. I mean, if you understand these, and all these reactions take advantage of electrical forces. Electrical forces is positive, is attracted to negative. Unlike charges attract, like charges repel. And so that's it. And so if you understand these, then these aren't so difficult to understand. Photochemical, a lot of photochemical reactions are redox. Some aren't. We can form radicals. Radicals are things with unpaired electrons. And but their behaviors can be similar in a lot of respects to what we already covered here. So if you understand these, then it's easy to understand these reactions here. Photochemical would be using light, chemical reactions. So the driving force is the formation of more thermodynamically stable products from less stable reactants. And so what we tend to observe is that things go from higher energy to lower energy. So I have this pen here. I'm holding this pen here. If I let go of this pen, is it going to go up or is it going to go down? If I let go of this pen. Yeah, it's going to go down. And so we're going from higher we don't call this chemical. We're going from higher potential energy, and we call that gravitational potential energy. The chemists aren't so interested in gravity because people don't hold beakers like this and then drop them, see what happens. But we're going from higher gravitational potential energy to lower gravitational potential energy, and the same thing in chemistry. We think of going from higher chemical potential energy to lower chemical potential energy. That would be a driving force in nature. And so this is what we're talking about here. And so what types of things? In terms of gravity, it's easy. The closer you are to the center of the Earth, the lower the energy. But in terms of chemistry, it's a bit more difficult. And so what types of things do we look for? The types of things that we look for is, for example, in metathesis reactions, we look for precipitation. If you get a precipitation, then you're forming a stable crystalline solid. Everything's packing together. Or gas, or weaker acid. Weaker acids are less reactive, therefore more stable than stronger acids. Stronger acids are like this, the pen up here, and weaker acids are like this, the pen down here. So that would be for metathesis. Now, metathesis driving forces aren't the same as redox. Redox is a different set of driving forces. For redox, we don't care if we get it precipitate. We don't care if we get a weaker acid. We don't care if you're forming a gas. In redox, the driving force is totally different. So an example of a redox reaction would be single replacement. In single replacement, it doesn't matter if a precipitate forms or gas forms. You're looking in single replacement to go from a more active element to a less active element. So it's going downhill like this. Or single replacement is just a single pattern. I'd like to think of redox in a more general sense. And the general driving force for all redox reactions are you're going from a stronger oxidizer to a weaker oxidizer, or a stronger reducer to a weaker reducer. That would be the driving force. So those are the types of things we look at. And so I divide it into 3 categories because we have essentially 3 driving forces. Although there's some overlap in the driving forces, which we'll talk about in terms of acid base here. And so metathesis, we look for things like precipitation, gas formation, weaker acid. Acid base is the same thing. We want to go from a stronger acid to weaker acid. And it's easy if we're dealing with Bronsted, because we have the acid base strength chart there. But if we're dealing with Lewis, then it's much more difficult because we don't have a Lewis acid base strength chart there. And so for Lewis acids and bases, we have to do a deeper dive into the structure and composition of the acids and bases to determine if we expect reaction or not. And then for redox, that's it. So we have 3 types of driving forces. There's some overlap here between metathesis and acid base. For Bronsted acid base reactions. That's it. So if there's a driving force, then we would predict that there's a chemical reaction that should occur between the substances. It says potential, which I'll talk about in a minute. But if we look at the types, so for redox, you know, just to help you get a better understanding, we have single replacement redox, we have skeleton redox. This is from chapter 5. We have redox chart method, which I'll talk about here, but that relies on some stuff like that redox chart on the left there. And et cetera, like combustion, you know, would also be a redox reaction there. For acid base, there are actually 3 definitions. So Lewis would be the entire universe of acids and bases. And then Bronsted-Lowry would be like a galaxy in the universe, you know. And the Arrhenius would be like a planet or a sun or a single star. You know, Arrhenius is so narrow, the definition, we don't even bother with that. We just look at Lewis and Bronsted-Lowry. And mainly Bronsted-Lowry because that's so easy to predict, but Bronsted-Lowry is just a small portion of the acid-base universe. But it's easy. For metathesis, double replacement are the most common metathesis reactions, but not everything follows the AB plus CD pattern. And so rather than looking at it in terms of double replacement, we look at it in terms of ion combination. Because we might have triple replacement, quadruple, quintuple, whatever, however many reactants we have in there. We're just looking at which cation and which anion are most likely to react with one another. That'd be it. There are a lot of variables, you know, when doing chemical reactions, like concentration, temperature, pressure, you know, lots of variables. And those can alter the driving force. So what we're going to do is we're going to be predicting reactions using these basic assumptions. The first assumption we're going to make is that the concentrations of all the solutions are going to be 1 molar. And the gases should be at 1 atmosphere or 1 bar. This is a little bit old. Some reactions happen at room temperature, some reactions happen at elevated temperatures, and some reactions happen at lower temperatures. But most reactions will occur at what temperature? At least you'll start them at what temperature? 0 degrees C? Do you do most reactions at 0 degrees C? No. Most reactions just are going to occur at whatever the temperature of the room is. And the temperature of the room depends on what you set the heat or air conditioning to. You know? And so what we're going to have is we're going to have an agreed upon room temperature. And what is the room temperature? 25 degrees Celsius or 298 Kelvin. And so I need to talk about this. The first basic assumption, some people might think, oh, those are standard conditions. But we have two standard conditions that we deal with. And they're right, that is standard conditions. And so our basic assumption, one, we're doing this under standard conditions. What are standard conditions? Solutions at 1 molar, gases at 1 atmosphere or 1 bar. But that is not STP. You know, STP stands for standard temperature and pressure. Standard temperature, do you know what standard temperature is? 0 degrees C. How many reactions have you done at 0 degrees C? 0. So when I talk about standard, I'm not talking about STP. I'm talking about something else. Standard temperature is 0 degrees C. Standard pressure is 1 bar or 1 atmosphere, depending on if they're holdouts. You know, this is like the metric system, but they're holdouts that it makes sense why there are holdouts here. I'm one of the kind of holdouts because 1 atmosphere is standard pressure, and standard pressure is the kind of the pressure at sea level at the equator of the atmosphere, you know. And so and 1 bar is not. 1 bar is defined differently. It's defined using some physics. Whereas 1 atmosphere is defined using some observations. What is the average sea level pressure of the atmosphere? And so, it depends. This is STP. What we're using here, and so this, my first basic assumption is this. I didn't write it like this, but the first basic assumption is we're going to use standard thermodynamic conditions. So what are standard thermodynamic conditions? Standard thermodynamic conditions are the concentrations are at 1 molar and the gases are at 1 atmosphere or 1 bar. So the concentration is 1 molar. Actually, I should put a little asterisk there, because it's a little bit different. Did I put a little asterisk there? No, I didn't. I said about 1 molar here. Why did I say about 1 molar? Because standard thermodynamic conditions are, it's not 1 molar. You know what it is? I'm not being 100% accurate here. It's that the activities are 1. And so really the activities are 1, but so few people remember what activities are that I don't bother saying it yet. Have you heard activities? Yeah. Okay, if you have an activity of 1, then it's pretty close to 1 molar. Activity is what we call the effective concentration of it. And if you go back to chapter 14, that's where they talk about activities. We're going to be talking about it more. And so, I forgot to mention that in the morning class. So the concentrations are about 1 molar, and the pressure of gases will be 1 bar or 1 atmosphere. Depends what table you're looking at. So it also depends on the date of the table here. So if we look at the redox chart here, this little footnote, these potentials are for neutral aqueous solutions. All other E naught values are for 1 molar ion concentrations and gases of 1 atmosphere. So you know this is an old table. Because a new table would say gases at 1 bar. Now, is there a standard thermodynamic temperature? there's no standard thermodynamic temperature. So temperature equals any temperature. But the most common temperature will be what? So the temperature can be any temperature because you can do chemical reactions at any temperature. You don't want to do all your chemical reactions at 0 degrees C, do you? No. So the temperature, well, it's a little warm today. Maybe it's 30 degrees C. Or what if the reaction happened in your body? What's body temperature?
37 degrees?
37 degrees C, 38 degrees C, what is it, 37? 37.1? Well, if you're a biochemist, you would do it under standard biochemical conditions. Under standard biochemical conditions, they would put out a temperature. If you're looking at human biology, they would put out a temperature there, but if you're looking at something like a reptile or something like that, then you know, they probably have a different temperature. But most of the thermodynamic tables are at 298 Kelvin. 298 Kelvin because that's what we call room temperature. And room temperature is 77 Fahrenheit, which is kind of warm, but that's it. And so that table on the left is missing that. That table if you look at the table in our book, our table in the book specifically states it's at 298 Kelvin. Because if you change the temperature, you're going to change the numbers a little bit. So our basic assumptions are, did I miss that? The concentrations of 1 mole in the gases of 1 atmosphere and the temperature is at 298 Kelvin. At least the starting temperature is at 298 Kelvin. Now, when we predict the driving forces, if we're using the redox chart over there and the chart method, then we have to be careful because extremely low or extremely high concentrations require compensating for. So if we have this is just a double replacement reaction, AB plus CD, forms, in this case, a precipitate of silver chloride and nitric acid here. The silver chloride precipitate is a driving force for metathesis reactions or double replacement reactions. So we expect a reaction to occur, we're generating a precipitate. But if we have very dilute concentrations, we get no reaction, nothing happens. We don't have enough to make a precipitate, even though we're reacting it. And so we have to compensate for that. Or very high concentrations is the same thing. Here there's no driving force because we go silver chloride plus nitric acid. Silver chloride plus nitric acid, what should it yield? It should yield silver nitrate. Well, all nitrates are soluble, so that's not a driving force. And hydrochloric acid. Well, nitric acid and hydrochloric acid, because of the leveling effect, have you heard the leveling effect? Nitric acid and hydrochloric acid are treated as being equal in strength. You know, even though when you look at the acid chart, which is stronger, hydrochloric acid or nitric acid? Well, look at the acid chart here, the Bronsted acid chart. Hydrochloric acid is stronger, but in water they're equal because water is base, and so they both completely react with water, and they form the same thing, hydronium, at the same concentration. And so, so there's no reaction here. There's no driving force. There's no precipitate. There's no weaker acid from a stronger acid, and there's no gas. However, if you add concentrated nitric acid, you might be able to get it to react. Well, we could try that, and it doesn't really react. But if you add hot concentrated nitric acid, then it reacts. And so with hot concentrated nitric acid, that will dissolve the silver chloride. But what you end up with is a mess of toxic gases that come out this thing. Gases like oxides of nitrogen come off, so orange plumes of gas come off this, chlorine gas, and other nasty gases that are quite toxic. But it reacts. And so we might have predicted no reaction, but it depends on the conditions. The conditions, the temperature and concentration here. This is a reaction that people do in Chem 1A and Chem 4. I try to demo this, but sometimes I forget to demo it. But it's lead-2 nitrate plus sodium hydroxide. It forms a nice white precipitated lead-2 hydroxide. But the very tricky thing about this reaction is it's like magic. You know, you add sodium hydroxide, you get more and more cloudy precipitate. And then as you keep adding more sodium hydroxide, the cloudy precipitate disappears, and it disappears rapidly. So just a few drops of too much of sodium hydroxide and the precipitate is completely gone. And what happens there is the excess sodium hydroxide here attacks the lead-2 hydroxide precipitate and forms this. This thing is weird. It's called trihydroxo or hydroxido, depending on what set of rules you use to name this. Trihydroxido plumate 2 ion, and it's an anion. And so what happens is we get a Lewis acid-base reaction that takes over here and dissolves the precipitate. So this is like the case of the disappearing precipitate. And normally we try to maximize the amount of precipitate by adding the maximum amount of precipitating agent. So if we add 1 milliliter of precipitating agent, we get the precipitate. But you might think, oh, might as well add 10 milliliters. We'll get the maximum amount. But if you add 10 milliliters, you get nothing. And so we have to watch out for that. And so, since there are so many variables, we want to keep it simple. So we'll just keep the standard thermodynamic conditions at 298. In 298, there's no standard thermodynamic temperature, but most of the charts we work with are at 298. Let's say it's this one. The charts in our book will label the temperature. Okay. I'm on low battery. Okay. And so we come up with a thermodynamic driving force. But you know, the thermodynamic driving force isn't enough. We also have to understand the kinetics. And so we spend a lot of time dealing with thermodynamics of this. You know, what's the driving force? How do we quantitate it? In Chem 1B, we want to calculate it. So for example, if we go from 1 molar to 16 molar, how does that change the driving force? Is it now going to be enough? Or is it still not enough? And so in Chem 1B, we might change the concentration and change the temperature. Now is it enough to drive the reaction? And so Chem 1B, we try to predict it quantitatively using thermo theory, in other words. But even then, we get a driving force. Like for example, we know that graphite is more stable than diamond. So diamond is less stable and it should fall down to graphite. In other words, it should decompose into graphite. However, the kinetics of this are so slow that diamonds are literally forever. And so if you have diamonds here, you let go of the diamond, it's not going to drop to graphite. It's just going to stay as diamond. And so it's going to be in this perpetually suspended state up here. And even though graphite is more thermodynamically stable, the diamond is what we call metastable. You know, it's permanently suspended here. It doesn't fall down because in order to fall down here to graphite, it has to climb a little hill here to get over, and it can't climb over that little hill. It's too much. And so we need to understand a little bit of the kinetics to properly predict if we're going to see a reaction or not. You know, how fast reactions occur is important. So we need to understand both the thermodynamics and the kinetics of these chemical reactions. All right, so we're going to start off with the first type of reaction here, metathesis. Metathesis, we have typically reactions of 2 or more ionic compounds, and we're looking at this. The goal is to find favorable ion combinations. So if you have a pot of ions, a whole bunch of different ions in there, you're looking for what ions like each other. What ions like each other are the ones that form precipitates, or the ones that form gases, or the ones that form weaker acids. So you're looking for those combinations. So it doesn't really matter how many, you know, like I could have something like this. You know the name of this? Silver nitrate. And then we know hydrochloric acid. What would you do in this situation like this? Well, this is a pot of ions. We have silver ions, nitrate ions, hydrogen ions, chloride ions, bromide ions. And in that pot of ions, we look at what ions like each other. And so from this, you know, I predict silver likes chloride and silver likes bromide. So either I'd predict 2 precipitates would form, silver chloride and silver bromide, or maybe 1 precipitate form, depending on the driving forces. In Chem 1B, we'd see, we'd be able to predict, do both precipitates form, or does one form, and then the other? If only one forms, which one is it? And so that's what we're doing in Chem 1B. But here all the other ions would be spectators, this particular example. But we aren't locked in, We could treat this as 2 AB plus CD problems, silver nitrate plus HCl, silver nitrate plus HBr, HCl plus HBr, or 3 double replacement type reactions, and see what forms there by switching over them. But, we could just keep adding more and more. So when we look at this from a theoretical, what do these share in common? They share stronger bonds. QM stands for quantum mechanics. So if we want to get into the theory of this, we look at the quantum mechanics of the bonds here, which we will be doing probably later. These are ionic compounds. These are all strong electrolytes. So they're all going to split up into ions, but sometimes we deal with weak electrolytes, like ammonia. And so if I threw in ammonia here, then what would I do? If I threw in ammonia, then I have one more potential precipitate. I have silver hydroxide as a potential precipitate. Now, how do I get hydroxide if I have ammonia in there? And then I have potential other things. I have this species too, which is kind of hard to see here, but this is the product of a Lewis acid base reaction here. I'd have this thing called diamine silver 1 ion. We'll learn how to name these things, but that's another potential. But this is not a metathesis. This is a Lewis acid base reaction here. And I said Lewis acid base are more complicated. So we'll start off chapter 24. This would be metathesis here. Now the silver hydroxide, where did that come from? That came from ammonia. Ammonia is a weak base. Weak bases are weak electrolytes. Weak electrolytes do what? Weak electrolytes, what most people say is that strong electrolytes completely ionize or break apart. Weak electrolytes, people say partially ionize, but bases don't ionize. Bases do something called hydrolysis. And so weak electrolytes partially hydrolyze. When we're looking at electrolyte properties, we're trying to understand what it does in water. Partially hydrolyze. So if we have some ammonia there, then we're going to have this Bronsted acid-base reaction occur here. This Bronsted acid-base reaction, Bronsted acids and bases are proton donors and proton acceptors. And so what are the products of ammonia and water? Ammonias are Bronsted base, waters are Bronsted acid. What are we going to form?
Hydronium?
We're going to form?
Hydronium?
Not hydronium, because that would mean waters are base. Bases are proton acceptors, but waters are proton donor. So if water donates a proton to ammonia, then ammonia is going to have 4 hydrogens now. And the proton's positively charged, so this whole thing has a positive charge. So we're going to form ammonium and hydroxide. Now, in Bronsted acid-base reactions, the driving force is to go from weaker to stronger or stronger to weaker. The driving force is to go from stronger to weaker. So this is our base, this is our acid. Now, looking over here, ammonium will be our product acid and hydroxide will be our product base. And so what's a stronger base, ammonia or hydroxide? Turns out hydroxide is stronger. Ammonia is known as a weak base, hydroxide is known as a strong base. So this is no reaction. This would be like a no reaction in Chem 1A, but in Chem 1B, we have partial reaction. And so in Chem 1B, this is going uphill. This is going uphill, and this is going downhill. So what this represents is this. This small arrow forward represents the small fraction of the entire population that can make it up the hill. Whereas this big arrow downhill means everybody can make it downhill. And so what we get is we get partial reaction. In other words, partial ionization or partial hydrolysis. But this isn't ionization in the typical sense. In the typical sense, when we think about ionization, like silver nitrate ionizing into silver ions and nitrate ions, that would be more ionization. This is hydrolysis, where we're going to have water react with it. Ammonia doesn't ionize. People try to ionize ammonia all the time. So people try to ionize it into NH2 minus plus H plus. Have you seen that? Or they try different things to ionize it. And so weak bases don't ionize, weak bases hydrolyze. And this hydrolysis yields a little bit of ammonium and hydroxide, and that little bit of hydroxide likes silver ions. And so silver ions like to combine with hydroxide. This is how I came up with silver hydroxide as precipitate, potentially. And so by understanding the different types of reactions, I could analyze this mixture without too much difficulty. In terms of having to memorize an excessive number of patterns. Am I out of time? Okay, I'm out of time here, so we'll stop here.